So chapter 2 brings us to the derivative of a function. And section 2.1 is we'll introduce the definition of a derivative at a certain specific x value and discuss that as a rate of change and also as a tangent line. So to get started, the first example asks us to find the equation of the line tangent to the curve y equals x cubed at the point 1, 1. So we don't quite have a formal definition of a tangent line yet, but so far in examples we've done in the past, particularly if we recall the dropping a ball off the stratosphere tower examples, we were finding the slope of secant lines and trying to approximate the slope of, a line tangent to a curve like this. So tangent essentially means just touching, right? So this line, this red line, this tangent line at the point 1, 1 on this curve touches the curve y equals x cubed at only one point, right? And that's the point 1, 1. Remember, this is y equals x cubed. And what we're looking for is the equation of this line. So we know one thing about this line. It contains the point 1, 1, right? Because that's where it touches the curve y equals x cubed. And if we know the point on this line, all we need to know next is the slope of the line. Or, alternatively, we could know another point on the line and we could use that to come up with its slope. But we can't infer another point on this line from this curve right here. So we've got to use the slope of this line. Well, the way we've done that or approximated that so far, right, we could estimate the slope of this tangent line by taking the slopes of secant lines. So I could draw another line through this curve that passes through this point, of course, but maybe also through this point. And I would connect these two more or less, right? And that's a secant line. It passes through the curve in more than one place, or two places specifically, and that makes it a secant line. And the idea and what we've done in the past is we've inched this line, this point, the second point, closer and closer to the point at which we wanted to find the tangent, the slope of the tangent line, until we got something that seemed to converge on a value for the slope, and then we just assumed or made the estimation that the slope was what it was. So now instead of doing that manually with a table like this, so we built tables that look like this, notice that the x values are approaching 1, in this case from above, and we could approach 1 from below. So from the right is what's shown, and then from the left we could do 0.9, 0.99, and so on, and estimate the slope of the line through these 2 points. So note that this point 1 f of 1 corresponds to this point on the curve, right? So 1, and then its output when we plug 1 into x cubed is 1. So 1, 1, of course. And this other point, f of x comma f of x, corresponds to all those other points that we're kind of taking guesses at and inching closer and closer to the x value of 1. And coming in from the left, we'd be down here as well. So that's really a limiting process. And we've got a few tools now from chapter 1 that help us calculate limits. So instead of putting a table like this together and having to take a guess every time, what we can do is take the limit as x approaches 1 of this whole slope function that comes from these secant lines. And that's what we should do rather than plug in values and try to come up with an estimation. We could probably get it exactly if things work out. Now notice if I look at this expression and say, I'm going to take the limit as x approaches 1. Well, I can't just plug in 1 because this function overall is not defined at x equals 1. We would have division by 0 for that slope function. So what we do is we'll have to manage it with a little bit of algebra. So the slope m of the tangent line, right, we're going to take the limit as x approaches 1 here, is equal to the limit as x approaches 1 of our secant line formula, right? Slope of the secant line formula. And we're sending x to 1. So what we're doing is we're finding the slope of this line exactly at this point right here via the limit. Now, again, once I fill these details in, remember that f of x has a specific definition. It's x cubed, right? So this will be x cubed here minus 1 cubed here. So I get x cubed minus 1. And then this is all over x minus 1. Okay. And now I've got a full fully explicit function here. There's no more f of x's in here, and I can start thinking about what this limit is and trying to evaluate it. So if we look closely at it, we realize again, just to point this out, I can't just plug in x equals 1 here, right? This is a rational function. It's not defined at 1, and we're taking the limit as x goes to 1. So I can't plug this 1 in to this function. So what I've got to hope for is that I get some kind of cancellation in this rational expression. And if you think about it, you realize that 1 is a root of x cubed minus 1. If I plug in x equals 1, I'm going to get a 0 in the numerator. If I plug in x equals 1 in the denominator, I also get a 0. So 1 is a root of both of these polynomials, which means that x minus 1 is a factor of both of these polynomials. So we can factor that x minus 1 out. So a nice way to do that is by synthetic division, since this is a linear root or linear polynomial, a linear factor of a polynomial. So you can line up the coefficients of x cubed minus 1. It would be 1, 0, 0, negative 1. And then you could use positive 1 as your root that you divide by instead of synthetic division, or likewise you could use long division, or you could remember the trick to how to factor a cubic polynomial. So multiple ways to do that. If you don't remember how to do that, I definitely encourage looking it up in probably a college algebra book or video or otherwise. So anyway, x cubed minus 1 factors as the following. It's x minus 1 times x squared plus x plus 1. So however you get there, synthetic division, cubic factors, or otherwise, you're able to factor this out. You could check that this factorization doesn't indeed, when you multiply it back together, give you x cubed minus 1. But the important thing is we notice that the numerator has a common factor with the denominator, and that's that troublesome function we were trying to get rid of to begin with, the x minus 1 in the denominator. So both those highlighted factors cancel, and we're left with only the x squared plus x plus 1 term, or function, or polynomial, which we're now taking the limit of as x approaches 1. Well, now we've arrived at a place where we can plug x equals 1 into this function, because of course the function we're taking the limit of is a polynomial. So when we do that, we have 1 squared plus 1 plus 1. So that's basically 1 plus 1 plus 1, and that's 3. So the slope of our tangent line at the point 1, 1 for our function y equals x cubed is 3. So we know now that this line has a slope of 3 thanks to this limiting process, which I think was a pretty intuitive thing to do, because that's how we were doing it with the tables all along, only now we've done it exactly with a limit. And I think we see that maybe these numbers were trending towards 3 anyway, so that might confirm that our method with the limit seems to be the accurate way to do it. And well, nonetheless, we know the slope, and we know the point 1, 1 is on this line. So I can write this equation as tangent line in point slope form, the point being 1, 1, the slope being 3. And remember that point slope form is y minus y naught, where y naught is the y value of the point. In this case, this value, the point 1, 1. Okay, and then that's is equal to m, our slope m is 3, times x minus x naught. And in this case, x naught is 1. It's the x value of our point, or the x coordinate of our point that we're interested in. And that does it. There's our equation of a line tangent to the curve. And we're going to do this quite a bit throughout chapter 2, find equations of lines tangents to curve, or tangent to curves. And pretty much every time we look for the slope, we're going to use a process that looks like this, or is a process that's completely analogous. And we'll learn how to do that as we develop more tools throughout the chapter. So let's properly define this tangent line. So in calculus here, we'll just define the line tangent to the curve y equals f of x at the point a f of a is the line through a f of a, right? So in the previous example, that was the point 1, 1, or 1, f of 1, and f of 1 was 1 cubed, so that was just 1, 1. Okay, and this line's going to have slope given by this expression. And well, this is the exact expression we just used. This is the secant line, the slope of the secant line for 2 points, a f of a and x f of x on the curve y equals f of x. And when we take the limit as x approaches a, well, we're finding the slope of the line tangent to the point A, f of A. Okay, so this is all provided this limit exists, and there are functions for which some values this limit will not exist. Okay, so to get back to the example of dropping a ball from the top of the stratosphere, we're asked a few questions. It asks us to find the instantaneous velocity of the ball after it's fallen for 5 seconds. Now we've attempted this in the past to get some estimate of what speed the ball is moving. And we probably did things like 5 seconds to 5.1 seconds, and 5 seconds to 5.01 seconds, or we did 4.9 to 5 seconds, or 4.99 to 5 seconds. And we made a table and we tried to estimate what that value was. Well, now with these tools in hand, we can probably find the exact slope or the exact instantaneous rate of change. Okay, so it turns out that the slope of the tangent line is also the instantaneous rate of change. Well, remember that velocity is the change in distance over the change in time. So instantaneous velocity is our change at 5 seconds. It's a change in height at the time 5 seconds. So yeah, to keep it simple, this is the instantaneous rate of change at the value A for the function f of x. So, and this is repeated down here, of course. So let's see, remember our position function is s of t equals 4.9 t squared. So this example is a little different from our formula. T is now our independent variable, so it's playing the role of x. So I'm going to rewrite this formula, but with s of t instead of s of x. So I'm looking for my instantaneous rate of change when a equals 5 at the time, 5 seconds. All right, so I'm going to take the limit as t approaches 5. This is where we're sliding our independent variable t, just like x, towards the value a. In this case is 5. S of t minus s of 5 over t minus 5. Again, every time we set this thing up, we won't be able to plug 5 in because the bottom term will be approaching 0. So we're always hoping to get some kind of algebraic cancellation, because that's really our only way through these until we develop more tools for them. So moving on, s of t, remember, is 4.9 t squared. That's what the function's rule is. So we apply it to t and we get 4.9 t squared. It looks just like it does up here because it's being applied to the same variable. S of 5, well, we plug in 5 for t and we have 4.9 times 5 squared. T squared is 5 squared this time. This is all over t minus 5. So the temptation to write these things out with 25 times 4.9, whatever those values are, is probably strong. I say resist doing that and notice that there's a 4.9 as a common factor in the numerator. And we could go otherwise. It just makes it harder to factor if we don't realize this step. But I can factor 4.9 out of this limit as the constant factor rule for limits, or constant factor law for limits, provided that this limit exists. Well, we're not sure of it yet, but if it doesn't exist, then we'll know that we should have never done this step, and maybe we declare the limit doesn't exist. But nonetheless, 4.9 factors out, and we're left with t squared minus 25 over t minus 25. And now we can start to see, okay, 5 is a root of the numerator and the denominator. We can also recognize t squared minus 25 as a difference of squares. T squared and 25 are perfect squares. So this factors as t minus 5 times t plus 5. Even if 25 wasn't a perfect square, it could factor as t minus the square root of that number times t plus the square root of that number, and we could still factor it similarly. Nonetheless, this is what we've got in the numerator, and we notice that t minus 5 cancels with t minus 5, numerator over denominator, and we're left with just t plus 5 in the numerator, or at all in this expression, and 4.9 is our constant factor out front. Well, the limit of this function as t approaches 5 exists, and we just plug in 5 at t plus 5. Remember, t plus 5 is a polynomial. So now we've got 5 plus 5, and all of that is times 4.9. That's 10 times 4.9. This is 49. And remember that our units are in meters, right? For this function up here. And this is meters per second. So velocity is distance over time. So at 5 seconds, this ball is falling 49 meters per second. We've probably seen in previous examples that this is approximately the case. right? If we've approximated near the time t equals 5. We've probably gotten close to this value, if not guessed it exactly as 49 meters per second, provided this was the function we were using. So that's our exact velocity, our instantaneous velocity, and this is a pretty powerful calculation to be able to do. There's a second question here that says the tower is 350 meters tall. How fast is the ball traveling when it hits the ground? Well, this one takes a little bit of thought to put together, because what we don't know is when does this thing hit the ground. So in other words, what's our A value? What are we approaching in terms of our A values, the time that it takes for this thing to hit the ground? Well, what we know is this: when it hits the ground, it has traveled 350 meters. So whatever time A that is, S of A is equal to 350 meters. This is what we need to find. We need to find the A value that satisfies this. Well, remember that S of A is 4.9a squared, right? Remember, that's what the function tells us to do with its argument. Square it and multiply it by 4.9. So S of A is 4.9a squared, and that's equal to 350. When I solve for A, I get sort of a disappointing looking decimal. It's kind of a messy number. Resist the urge to convert this thing to a decimal with a calculator. Keep it as is. It's a number, and we can do calculations with it as that square root of 350 over 4.9. I didn't take the negative value of A. If you think about that for a moment, you'll realize why. And when I took the square, I divided by 4.9 on both sides, and I got A squared equals 350 over 4.9. When I took the square root, I should have introduced plus or minus in front of the square root. Why wouldn't I do that? Well, remember that we're talking about a practical example. Time is only moving forward in this, right? So this should be a positive number of seconds after I've dropped the ball, not a negative number of seconds. That would be going backwards in time. So we only use the positive version, or the positive value of A. Okay, so now we have a value for A. That's what t is going to approach. So we're trying to find the instantaneous velocity of the ball when it hits the ground. So how fast is it going when it hit the ground? Now, this is the limit as t approaches this value of A, and it's the same function. S of t minus this S of A being this value now, over t minus A. Okay, the number is just a little bit clunkier with that big square root in there, but notice when I kept it as is and not writing it as a decimal, some things will cancel. Notably, this square root and square will cancel if I wanted to, but we're going to do something slightly different. I'm going to factor 4.9 out of both these terms, just like we did in the previous part of the example. So when I do that, I'll have t squared minus this number squared. So that's a difference of squares again. So in other words, it could be t squared minus 350 over 4.9. When I factor it as a difference of squares up here, that's what I suggested before, it's t squared minus 350 over 4.9. Well, that's t minus the square root of 350 over 4.9 times t plus the square root of 350 over 4.9. Again, if you're not sure of that, you could just call this thing A, right? That could be the number A, or this thing could be the number A here. And t squared minus capital A is t minus square root of capital A times t plus square root of capital A. It's just the difference of squares all over again. The numbers are just a little messier. Okay, the denominator just remains as is, but when we make this factorization, we realize the same thing that happened above happens here. We get a cancellation with the denominator, and we absolutely need that because we can't go plugging this number in for t because the denominator is 0. So this cancellation leaves us with t plus the square root at 350 over 4.9 as t approaches this number in the limit. And what we end up with is we just plug this value of t in right here. So we'll have two factors of root 350 over 4.9. We add these two together times 4.9. So here's 4.9 times 2 times this value. All right, so this is 2 of these. And that's 9.8 times square root of 350 over 4.9 meters per second. Now, mathematically, I like this number better. This is exact. It has all my information in it. I don't want a decimal most of the time, right? A decimal is more practical to see, to get an idea of what the velocity is, but this is probably roughly, I think when I did a mental calculation to see what it comes out to, I think it came out to about 100 meters per second. So if you wanted to put it into a decimal and get the approximation, you can go for it. But this is the exact answer. Decimal answers are always approximate answers, unless the decimal, is finite and not just truncated by the calculator. So nonetheless, I would express your answers, however the homework or problems you may encounter ask you to. This problem doesn't specify, so I left that as a very exact, in its exact form with the radical. So that's how fast the ball is moving when it strikes the ground after traveling 350 feet and obeying this this law right here, or this function here. So there's another name for this tangent line calculation, right? It's also called the derivative of the function at a. So let's have a look at a formula for that. And there's a connection from this formula to the last one, okay? So we introduced this formula here when we define the derivative, but we'll note that it's the same exact formula as that secant formula with the limit that we've been using for the last two examples. And I'll show you when we're done with this example. But this is a more convenient formula to calculate the derivative with often. So we'll tend to use this more often when we calculate derivatives by their definitions throughout the first few sections of this chapter. So f prime of a, this is a new notation, right? So now instead of calling it m, the slope of the instantaneous rate of change, or the slope of the tangent line, we're going to give it this new notation f prime of a. Remember that f prime of a is still just equal to m. This is the same thing we've been calculating. This formula is just slightly different. Okay, so the derivative of f at a is f prime of a, and that's equal to the limit as h approaches 0 of f of a plus h minus f of a over h. Now you probably encountered this expression without the limit in it back in college algebra course, or hopefully you have. This is called the difference quotient. Okay, so we'll evaluate this difference quotient as a limit as h approaches 0, and if it exists, if that limit exists, then we know that we've got the derivative of the function at a. So let's have a look at the first example. It says find the derivative of the function f of x equals x squared minus 3x at the number a. So a now is not some, it's not 1, it's not a 5 like we did in the previous situation, right? It's not root 350 over 4.9. It's just some general number a, which this is a nice extension into what we'll do in section 2.2. So f prime of a, we're just taking it for granted that a is some number. Well, it's the limit as h approaches 0 of f of a plus h minus f of a over h. So f of a plus h, my first function is in these brackets right here. Okay, so what does f do to its argument? When you hand it an x, it squares it, and then it does minus 3 times it. Okay, so we're handing f a plus h here, so it squares it, and then it subtracts 3 times it. Right? So everywhere I have an x, I replace it with a plus h. I find that it's really useful to put these parentheses everywhere there was an x up here, and then apply the function to those parentheses, right? So square the parentheses and then minus 3 times the parentheses. And that helps you get right all the terms that need to fit into these parentheses here. The second part of this is a little easier. F of a, well, that's just swapping out x for a, and we get a squared minus 3a. That's not too bad. Now, we can't just plug in h equals 0 to this limit, we see, because the denominator would be 0. This is very similar to what we had before. It's our first hint that this formula works the same as the formula we were using before to calculate these instantaneous rates of change, or this derivative. So what we need is a cancellation. We're hoping to find that up here somewhere. So remember, when I square this binomial, to be very careful. It's the first a squared plus the inner a times h times the outer h times a plus the last is h squared. So there's 2 a times h terms. So that adds to 2AH. If you need to, write down both A plus H times A plus H and do all the algebra necessary to come up with this trinomial from that binomial squared, right? 3 terms from 2 terms squared. Next, we have -3 times A plus H. We get minus 3A minus 3H. And then we've got minus everything inside here. So we have to distribute that minus sign. Be careful with that as well, or else you won't get the cancellation. We have minus A squared, and then minus minus gives us a plus 3A. So now all these terms are laid out in the numerator, and we see that some things add to 0. This is typically going to be the case in these problems. A squared and negative A squared add to 0. Negative 3A and positive 3A add to 0. And what we're left with, we realize, are terms that only terms that have a factor of H in them in the numerator, which is perfect because that's what we need in order to be able to cancel the H in the denominator. And so we're ready to do that, and that's what we do in the following step below. So all the H factors of H is canceled out with this single factor of H in the denominator. And what we're left with, notice that one factor of H survives. H squared becomes H to the first. And otherwise, 2AH and negative 3H lose their factors of H. And we're left with this expression. And now we're taking the limit as H approaches 0. And notice this about this limit. A is a variable, and it might make us nervous to take the limit of an expression that looks like this, but H has nothing to do with A. A is some constant, some other real number that is not H at all, right? So it doesn't do anything. It's a constant with regard to this limit. So the limit as H goes to 0 only affects this part of this function. And that, of course, goes to 0. So what we're left with for this limit is 2A minus 3. And that's our answer. And this is a powerful tool now, because now if I said, what's the derivative of this function at A equals 2, we have a formula that tells us how to find it. We just plug in A equals 2 right here, and we'd have 2 times 2 is 4 minus 3 is 1. So we know the slope of the tangent line at A equals 2, where this function f of x is 2, or sorry, 1, right? Once we plug that in and calculate it. So this is a pretty powerful general tool, and it's the way we're going to use the derivative more often than not in the future. So what's the connection between this formula and the one we worked with previously? Notice this thing. As H goes to 0, our denominator goes to 0. That was the same when X went to A, X approached A here, right? Our denominator went to 0 as well. So that kind of begs this substitution. It says, well, why, X minus A is sort of playing the role of H. So H is equal to X minus A. And so we're going to convert this formula into the other one by doing that. H is equal to X minus A down here. So here's my notes on doing that. And we could comment then, well, if H is equal to X minus A, and if we solve for X by adding A to both sides, X is equal to A plus H. We'll see why we do this in just a moment. And then we observe then that as H goes to 0, the limit as H goes to 0 of H is equal to 0, right? So this is true. Okay, and also the limit as X goes to A of X minus A, well, that's equal to A minus A, and that's 0 as well. So these two limits are equal to each other, so we can swap the limits out. This limit can replace this limit. As long as everywhere there's an H, I now have an X minus A. And alternatively, everywhere there's an X, I need to put an A plus H. So that tells me exactly how to change my original formula to the new formula. So here's our original formula. Limit as X approaches A is now swapped out by limit as H goes to 0, because those two limits are equal to each other, provided I make all my other substitutions. And when I look at this X, I now know that X is A plus H. So this X becomes an A plus H. And then minus f of A, well, there's no X in that, so this just stays the same. And then in the denominator, I've got X minus A, and I know that X minus A is equal to H, so I replace that with an H. So it turns out that these two formulas are exactly the same. So we can use either one to calculate the derivative of f at a. So we'll call it f prime of a. They're both the derivative of f at a. Now, which one's more useful? Typically, this formula is easier to use to calculate these derivatives in practical examples like the ones above, but we've seen both of these actually work, right? We saw this formula work for some functions, and we've used this one in the current function, the current example on this page. So typically, I would suggest to use this one when you need to find the derivative by the definition, but it could be, in some cases, easier to use the earlier one that was given. So the last problem we'll do here is we'll use all our tools to find an equation of the line tangent to the curve f of x equals x squared minus 3x at the point 1, -2. So find the equation of the line tangent to the curve at the point 1, -2. All right, well, notice this function, f of x equals x squared minus 3x, that's the same function we were just working on. We just found its derivative. We know that f prime of a for this function, for any number a, is 2a minus 3. And that's defined anywhere this function here is defined. Well, that's a polynomial, so that's defined everywhere. So it turns out this function has a derivative for any value of a, which is really nice. So let's use that. So the slope of this line, tangent to the curve f prime of a, is 2a minus 3. That was our derivative that we found for f prime of, or for f in the previous example. So the slope at a equals 1, we plug in 1 here for a, f prime of 1, in other words, is 2 times 1 minus 3. And that's what we have right here. And that's 2 minus 3. So that's -1 is the slope of the tangent line. So the hard part's now out of the way. We did all the work for that really in the previous example. So we know a point on the line because 1, -2 is where we want the tangent line to be located in its tangency to our original function. So 1, -2, so this is our y coordinate, this is our x coordinate. So y minus -2 in point slope form is the left-hand side, and that's equal to the slope, which is -1, times x minus 1, our x coordinate. And there's point slope form. And maybe some questions want your answer in point slope form. Simplifying this a little bit would be y plus 2 equals -x, negative parentheses x minus 1. They might want your answer in slope intercept form. Remember, that's easy to get to. You just have to distribute this factor of a -1 across this term and subtract 2 from both sides and simplify. In that case, you should arrive at y equals -x minus 1. So there's slope intercept form. Remember, this one's called slope intercept form because this is the slope of the line, -1, and this is the y-intercept of the line, also -1. So there it is. Those are that's section 2.1, a full rundown of finding the line tangent, the equation of a line tangent to a curve. We've gone from possibly approximating what the slope of a tangent line to a curve might be to having a very exact and precise rule for it, either via this formula or its equivalent formula here. So as we progress, we're going to find a way to calculate this derivative without doing all the work of the limits. But we don't really ever want to forget that this is exactly how the derivative is defined, and that this limit is an important situation when we're not sure how to take the derivative of a new function. This definition will help guide us through that. So section 2.2 will talk about the derivative as a function of x now instead of a function of a, and that's when things will really start to look more like calculus generally does.